Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay, boleh dengar saya ya? You guys can hear me. Right, good. Okay, so what we are going to do today is, as usual, we have two sessions for Tuesday class. But our first session, we will go through again what we have learned, and then maybe we will do one or two examples. Okay, because from the last class, so I get some feedback that some of you still a bit confused on something on Z transform topic. Okay, so actually that's why it is important that you fill in the attendance form, because you will give me some feedback on which part that you really understand, which part that maybe you are still a bit confused about it, right? So okay, because of those response, so I will do maybe I think two example today. Okay, before we go to the next topic, which is inverse Z transform. Okay, so but before that, so as usual also, let's do some recap what we have learned so far. Okay, all right. So you have seen this one, but let's just do the recap. So what we are going to learn in this course is actually we will focus on LTI system, but of course in our first 2 weeks, so we are actually focusing on a more general system, which is also the non-linear and non-time invariant system. So we are checking it, either it is linear or not linear, either it is a time invariant or not time invariant. But starting from week 3, so we focus on LTI system, so which is a linear and time invariant system. Okay, and actually to be more specific, actually we are what type of LTI system? So we are actually focusing on filtering implementation. Okay, so we will see that what is the filtering later. So, and what we have here is, so this is the one that we have seen that on chapter 1. So we have seen what is a sampling from a continuous signal into a discrete time signal. And then of course, this is a system. Okay, so what is a system? So a system is you have an input, and then you do something to the input so that you will get a new form of signal as an output. And for LTI system, so we have what we call a filter, or this is what we call an impulse response. So we have seen this, which is an impulse response. And we already know that there are two types of impulse response, which is one is FIR, finite impulse response. So this one, and then this is infinite impulse response. So this is actually in chapter 2 and 3, and we have seen so how to solve this LTI system. Okay, so if you have FIR system, so you have an option, either to do convolution to get the outputs. To get the outputs, either you do convolution or you solve the difference equation. But for IIR, so you cannot do the convolution. So what option that you have is only you can only solve the difference equation. Okay. And then, so we have done analysis. So what kind of analysis for LTI system that we have seen so far? So it is on stability and causality test. Okay, we can test stability and causality for LTI system. It doesn't need to test the linearity and time invariant anymore, because it's already linear and time invariant. So that's why we are focusing on the other two, which is stability and causality. And we have seen 3 methods on how to test this stability and causality. And this is actually on a time domain. So the 2 of the method is actually from time domain. So we have seen on, this is based on difference equation for stability. And this is for causality based on a difference equation. Okay, now we have those terms. So you need to get used to those terms. So we have a difference equation. And then another one is we have that Hn. This is what we call impulse response, this one, impulse response. Okay, so and then we have those kind of tests. So for example, stability, checking on impulse response. What should you do is just you sum all the values inside that the values on the impulse response and check. If it is non-infinity, then it is stable. Okay, and last week, so we have seen, which is in chapter 4, on how to do Z transform. And why we do Z transform? Because Z transform is actually transforming our signal in time domain into another domain, which is maybe most of the time, it is more favorable. So we can design it better because of the maths, Okay, and we can see something else. Okay, we can see something else. So maybe it's quite limited. What can we see in time domain? So we need to transform it into another domain so that we can see other things, right? And plus, again, the maths is normally easier. So compared to the time domain. So that's the purpose of why we do Z transform. Okay, and we have seen another methods on how to check stability and causality based on ROC. So we have seen on how to check stability and causality on difference equation. This one. So this is on difference equation, and then this is on impulse response, and this is on ROC, the region of convergence. Stability unit circle must be inside the ROC. Causality, it must be a right-sided ROC, which is the ROC must be a Z greater than. Okay, so if you see ROC of a Z greater than, then it is causal. Other than that, it's not causal. Okay, so and we have seen a bit on this one, which is the poles and zeros. So how can we find the poles and zeros of a Z transform? Okay, and today we're going to look at another example, okay, so that everybody will be clearer on how to get those poles and zeros. Okay, any questions before we start? So let's do, because we have a lot of questions here, so we will do one of it. So we have done this one, okay, last week. So today we're going to do number 14. Okay, so we'll do number 14. Okay, let's see what is the question. The question is we have a Hn, so we have Hn, which is equals to 2 to the power of n u minus n. Okay, so this is actually a folded version of unit step. Okay, what is the un? Un is a unit step, but this is a u minus n. So this is a flip version. And plus 0.8 to the power of n un. So we will find Hz, and then what is the ROC, and then the poles and zeros. Okay, for this one. Okay, so let's start. So what is, I'm going to write it again. So what is our impulse response? It is 2 to the power of n u minus n plus 0.8 to the power of n un. Okay, so before you can do the Hz, so maybe you should be able to imagine. So how does this signal looks like? Okay, 2 to the power of n u minus n. So how does it look? We know that this is un. Okay, so this is un. So from 0 up to infinity, the value is 1. Okay, so this is un. So if you want to have a u minus n, so means that you need to flip this one. Okay, you need to fold it. So after you fold, so it becomes, this is 0, minus 1, minus 2, up to minus infinity. And everything is 1, so this is u minus n. And what is actually 2 to the power of n? So you should be able to imagine that also. And that one supposed to be 2 to the power of n is at 0, at n0. So this is n, this is n. 2 to the power of 0 is 1. Okay? 2 to the power of 1, 2. And then here you will get 4 up to infinity, you will get infinity. And it doesn't stop there because it doesn't give a limit because this is a 2 to the power of n. So at minus 1, so this is actually 1 over 2. At minus 2, this is 1 over 4. If you goes up to minus infinity, so this is close to 0. Okay, so what is this? So this is actually 2 to the power of n. So what we have here is 2 to the power of n multiply with u minus n. So which one that we need to multiply? This one. This is u minus n multiply with this signal. So it means that all those values from n equals to 1 up to infinity will be multiplied by 0. And the rest, which is from 0 up to minus infinity, will be multiplied with 1. So what will you get is actually, this is from minus infinity up to minus 2, minus 1, up to 0. So this is 1, this is 1 over 2, this is 1 over 4, and then this is very close to 0. The rest will be 0. Okay, so what is this? This is 0, 0. Because you multiply with 0. Okay, so try to do this, try it yourself. Okay, you should be able to sketch this, 0.8 to the power of n un. Okay, so now we have, so what we have is actually a range from minus infinity up to 0 of 2 to the power of n. And basically, if we look at this equation, so this is actually un. So un is the ranges from 0 up to infinity. So that actually we have a value from n equals to 0 up to infinity for 0.8 to the power of n. Okay, so that is actually in time domain, but we need to transform it into a Z domain. So I'm trying to search for some space. Okay, continue from a quiz question 14. Is it 14? Yes, okay, 14. Okay, so let's do that. So write it again. Hn is actually equals to 2 to the power of n u minus n plus 0.8 to the power of n un. And what is the hz? So hz is actually just a summation. So this is the formula. Summation from where? From minus infinity up to infinity, of course. Okay, the whole range of hn z to the power of minus n. Okay, so this is a z to the power of minus n and hn. So where is the hn? So this is our hn. So what we have is you just plug in the value, the hn. So this one becomes 2 to the power of n u minus n plus 0.8 of n un of z to the power of minus n. And we can separate those two because this is just a plus. Okay, this is a plus. And what we get is actually a summation of, this is, we already know that this is actually the ranges from minus infinity up to 0. So this is from minus infinity up to 0 of 2 to the power of n z minus n. Okay, the first term. And the second term is, this is n from 0 up to infinity of a 0.8 to the power of n z minus n. Okay, so we can expand that so that now we have two terms, because this is just a plus. And from last week, so how can we do this? So actually we can do this, n minus infinity up to 0 of 2z minus 1 to the power of n, plus n from 0 up to infinity of 0.8 z minus 1 to the power of n. So what is inside that bracket? That one is what we call a common ratio. Okay, because this is very important, because we need to check for convergence. So how do we check convergence? Is from this common ratio. So that's why we group it into that. We put it into a bracket. Okay, because this is the common ratio. And from here, from the equation of Hz, and this is actually a geometric series. Okay, a summation. A summation of a sequence or geometric sequence is a geometric series. And we have a solution for geometric series. Okay, you have seen the videos. So if you forgot how to do it, so just watch again that video on the geometric series. So how do we solve this? And what we get is actually whatever inside the common ratio. So which is, this is 2z minus 1 to the power of minus infinity plus this is 2z minus 1 to the power of 0 plus 1. Okay, and then divide. Sorry, this is not plus. This is it plus? Wait, I forgot. Is it plus or minus? Anyone remember? So that we can have it faster. Minus. So just to make sure. So where is the formula? Where is the formula? This one. Okay, minus. Okay, this one. So actually it is from this formula. So minus. And no worry, actually you doesn't have to remember any equation. Okay, in test and exam, if the equation is needed, so the equation will be given. Okay, then, so this is actually minus. And this is actually 1 minus the common ratio. Okay, so this is for the first one. And for the second one, so this is 0.8 z minus 1 to the power of 0 minus 0.8 z minus 1 to the power of infinity plus 1 divided by 1 minus z 0.8 z minus 1. Okay then, and okay, let me put this properly. This is minus infinity. And to make sure that this term is converge, so we need to make sure that, because this is the one that we have to the power of infinity, and this is actually minus infinity. So this term, this common ratio, supposed to be greater than 1. So this one, the common ratio, supposed to be greater than 1. Okay, it needs to be greater than 1. And this one, because the one which is because this one to the power of 0 is simple, this one becomes 1. But this one, so you have to the power of infinity. So to make sure that it converge, right? So that's 0.8 z minus 1 supposed to be less than 1. It needs to be less than 1. Okay. So because of that, and then we know that, okay, we bring this here. So if this is a converge, and this is greater than 1. So what will happen is this one will become a 0, okay, very close to 0. So this is going to be very close to 0. So then you will have a 0 minus, and this one. So this is a 2z minus 1 to the power of 0 plus 1 to the power of 1. 2z minus 1. Divide 1 minus 2z minus 1. Plus, and if this is less than 1, so to make sure that it converges, this one becomes 1. This one becomes 0. Okay, so we have 1 divided by 1 minus 0.8 z to the power of minus 1. And what is the ROC? The ROC is, so if we look at this one, so this is 2z minus 1 greater than 1. So z supposed to be less than 2, right? So that one is z must be less than 2 for this one. And this one, if you manipulate the equation, z supposed to be greater than 0.8. Greater than 0.8. So that will be the ROC. ROC is z from 0.8 up to 2. Okay, so this is, and if you want to sketch the ROC, so this is going to be the ROC. So first you need 0.8, and the other one is 2. So you should have 2 circles. And these are the region of convergence. This is real. This is imaginary. Okay, so what is this? So this is z plane. Okay, so we have that one. So now what we have is hz. So next, so what is this? So this is we need to wait. It's lagging. Okay, so this is actually hz. Okay, so that's the result. So now next we will before that let's look at this one. So is this stable? Is this stable? Okay, what is the stability? Anyone remember? So please answer that one. Is this stable?
When the unit circle lies inside ROC.
Yes, true, correct. So then we can conclude that this is stable because ROC is somewhere here. So this is the 1. 1 is here. Stable. Is this a causal? Does it causal? So, okay, stability, we already know it. Does this system causal? So how to check that? How to check on ROC? So please, someone. You need to check the ROC. Check this ROC. So is there any indicator that this is causal or not causal? So how do you check that? Come on, come on. So you can write it. You can write it on the chat section also. If he doesn't want to speak up. Come on, come on. We need to move on. Someone need to answer this.
Is it because it's a ring shape, so it's non-causal?
Yes, true. It's non-causal. It's a ring shape.
Sir, it's actually non-causal.
It's actually
Not non-causal, right? Because
yes,
it's
not causal.
Because it's a combination of anti-causal and causal.
Yes, true. Exactly. Okay, that's accurate. That's accurate. Because it is a combination of actually right-sided and left-sided, or a combination of causal and non-causal. Actually, this is causal. This one is causal. This is not causal, but because it is a combination of causal and non-causal, so it becomes non-causal. And if we look at this one, so this is a z less than. So we doesn't want that. This one is a Z greater than. That one is a causal, but this is non-causal. Okay, and we can see that also this is a ring shape. So causality is only when you have ROC of a right-sided, so it's going outside. Okay, so so we know that. So next will be what will be the poles and zeros? The poles and zeros. So what's Hz that we have is this one is minus 2Z minus 2Z minus 1 divided by 1 minus 2Z to the power of minus 1 plus a 1 divided by 1 minus 0.8Z minus 1. Okay. So what is a poles and zeros? A poles is actually roots of the denominator. So we need to combine this equation, okay, these two terms, so that we can see what will be the roots. Okay, and what is the zeros? Zeros is the roots for numerator. So after we combine both, so we can see what will be the numerator. Then we need to find the roots for it. Okay. And to do that is actually quite simple. So what you can do is the denominator is just 1 minus 2Z minus 1 and then 1 minus 0.8Z minus 1. Okay. And this one you need to multiply. This is minus 2Z minus 1 of 1 minus 0.8Z minus 1 and then plus 1 minus 2Z minus 1. And we doesn't have to do anything here because we already know that this is the roots, right? So one is 2, another one is a 0.8. So that is actually the roots. So because this one we already factorize it into a Z to the power of minus 1. We need to solve the numerator. And from there we have minus 2Z minus 1 plus 2 multiplied 0.8, 1.6 Z minus 2. Okay, this is Z minus 1, Z minus 1, Z minus 2. Plus 1 minus 2 Z minus 1 of the rest. This is 1 minus 0.8 Z minus 1. And let's see, so this is that is a 1, this is 1, and then this is to the power of minus 1, so we have minus 2, and this is minus 2 becomes minus 4 plus 1.6 Z minus 2. Okay, so we already know that what is the poles? Poles is a Z equals to 2 and Z, let's say this is a Z1, Z2, another one is a 0.8 because this is already factorized. Okay, now try to do this. Use your calculator. So what will be the roots of this numerator so that we can have our zeros? So we should have 2 zeros. Okay, so what will be the Z1 and what is the Z2 for zeros? Okay, so do that now. So and let's see. So what will be the what will you get? So you should have 2 roots because this is to the power of minus 2. Okay, I give you 1 minute. 1 minute. So I got the rest 1 minute. If anyone confused with any of the steps, so let me know, okay? So I can repeat. The step. No worry. Okay, finish. So let's see what is the Z1 and Z2 for zeros. So we should have 2 zeros. Still remember how to use your calculator? So if you don't remember, so please watch. There's one video in e-learning on how to find roots. All right, someone please. So that we can finish this example and move to another example. Z equals to 3.54 and the other one is 0.45. Okay. So any other answer? Any other answer? Same thing?
That equals to 2.2.
2.2. The other one?
0.3. 0.3.
2.2, 0.3.
Yeah.
Okay. Okay, let's see. I have a big calculator here. Okay, so this is called MATLAB. So let's see. So which one is what I can do is I just use function roots of, let's see what is our 1 minus 4, 1.6. 1 minus 4, 1.6. Okay, so let's see. So the answer is 3.54 and 0.45. Okay, so make sure you guys get these numbers. So a lot of answers here. So this is a 2.2, 0.28. Okay, the first one is 3.54. Okay, so first one from Connie is correct. Okay, so if you don't get this answer, so please try again using your calculator so that you can get this value. So it's very important, right? It's very important. So the answer is supposed to be 3.55. So we can get that one, 3.55, 0.45. Okay, again, I always forget. 355, 0.45. So 3.55, 0.45. Okay, so those are the poles and zeros. Right, so it's actually quite simple. It's just you need to know how to use a calculator, finding roots of the numerator and denominator. Okay, so any questions? Any questions? So our next example will be on MATLAB. Okay, so this is going to be the first time I'm going to use a MATLAB in this class. Okay, I need my keyboard. Okay, sure, no questions. Hopefully everybody are clear on how to do the transform from time domain into a Z domain. You get a HZ and the ROC. The other one is the poles and zeros.
Inshallah, Doctor.
Okay, very good. So okay, so this is a MATLAB. So I think everybody already if familiar with MATLAB. Okay, so at least you already use this MATLAB in your first year course scientific programming. So that is actually, I think, the first time you use the MATLAB, scientific programming. And then I think several courses you are also using this MATLAB. Okay, because this is a quite a good software to do some simulation. Okay, so let's say now if you go to your e-learning, so I'm going to use this your assignment. So you have one signal which is the ECG signal. Okay, I'm going to use this signal. okay, and show you how we do this filtering. So what is the MATLAB function that we have? So we have a conv. So we have a filter, but if it is FIR, we can use conv. We can use filter also. If it is IIR, so you cannot do convolution, right? You just need an option to use filter. And this is how to plot. Let's make this a bit bigger. So how to plot a signal if you have a signal. So actually you can do the plot n over fs. So what is actually n over fs? So this is actually t. T is in second, time in second. What is n? N is a discrete time. Okay, so it is an integer. N is integer. So let's see. So we're going to plot that and then do filtering and observe the output. Okay. So in this example, so okay, I'm going to clear that and this is actually what we call a workspace. Workspace will have all your variables loaded to MATLAB. Okay, so whatever the value that you need, so actually you need to load it into MATLAB. Then we can process it. And of course, so if I ask you, so where does this start? So this is where it is stored in RAM. So it's not fixed. Okay, when you close MATLAB, so it'll be gone. So this is actually in RAM, not in ROM. So first I'm going to load my signal, so which is ecg2.mat. I'm loading it. So this is my signal now, ecg2. So how many samples that I have? 2000 sample. Okay, so we have a 2000 sample here. And because we have a 2000 sample, means that our x-axis, which is the n, because we start from 0, so it should end at 1999. Okay, one value before 2000. That's our n. And now I can plot it. So using my n and my signal. So this is the ECG signal. So it's quite noisy. Okay, so we can see that this is quite noisy. So it's not clean. So it's not clean. And then because this is using n, so this is actually a sample 0 up to sample. Actually, the last one is at 1999. Okay, so but of course we can always map that into a t. So what is a t again? T is actually equals to n over fs. And if you go to if you click this, so actually it is stated here, the ECG signal, the frequency sampling is 200 Hertz. Okay, because it's already given. So whenever you have a signal, you should know what is the fs. You should know what is the fs. Okay, what is the fs? Fs is actually equals to 200 Hertz. So this is our fs. And then t, what is a t? T is just n. So we already have our n. This is a n over fs. Okay, that's simple. So then we can do, let's try to plot that again, not with n, but now with t, so that we can see x-axis in second. So now we know that actually this ECG signal is taken, is recorded for 10 seconds. Okay, for 10 seconds. So this is the first second. So this second number 2, the third second, until the 10th second. Okay, so this is what we know already. And in this example, so we will use our impulse response, which is normally we denote it as a H. Okay, and at this stage, the H is the impulse response is given. So we don't get to the chapter on how to design it yet. So everything's supposed to be given to us. So and let's say this is the This is our HN. Is this FIR or IIR? Our impulse response here. So this is the most important thing now. One of the important things. FIR or IIR? So you should be able to answer this easily at this stage. FIR, yes, correct. Because we can count that. So this is just 1, 2, 3, 4 samples. So what is the length? The length is 4 samples. Finite. It's not infinity. Okay. So so after we have this H, so actually we have everything already. So how to do filtering? So we just need input, and then we have the filter. So which is the impulse response, HN. And because this is FIR, so you can choose either to do convolution or difference equation. If you want to use a convolution, so you just do this, CONV. If you want to solve difference equation, you do this, filter. Okay. So, but of course, you need to identify what is the B and what is the A. And for FIR, it's quite easy, straightforward. So we have seen that. Filter coefficient B is actually equals to HN. And A is equals to 1. Okay, for FIR. A is fixed, equals to 1. And your HN is equals to B. So we already know that this is actually H and this is 1. If it is an FIR filter. Okay, let's try to do that. Y, so what is Y? Let's do convolution first, CONV. Your H and then your signal. Okay. And because it is a LTI, so actually this is, of course, you can do this also. Right, ECG2 first, and then H. It doesn't matter. Right? It doesn't matter. It's finished. You have done that. So you have done the filtering. Because that's the process. The process, what is the process? The process is convolution. So let's see what is Y. So Y, so we have the number of samples is 2003. So a little bit longer compared to the input. Okay, because this is the results of convolution. Then we can say that let's say this is our N and Y, because I already use N here. So let's say I'm going to use NY here. So let's say this is starting from 0 up to, it's supposed to be up to 2002 because our sample is 2003. Okay, then we can plot that. So what will happen here? Let's see what is the output. I'm going to use NY and then Y. So this is actually have been filtered. So compared to this one, this is quite noisy, and this is looks clean. Okay, but it is good. Is this good? So we haven't get into that yet. So we will do the analysis later. Okay, but this is actually the results of filtering. So how you do it? Just do convolution. Just do convolution. Okay, and you can do the same thing using filter. Let's say this is a Y2. Do the filter. Because this is FIR, the B, this one, B, that B is H. And what is the A? The A is 1. So we already know that. And then you should put the ECG, because that's our input. So you should get the same thing. You're actually getting the same thing. Okay, so either one. So you can use CONV, you can use filter. So what is the difference? So the first one is actually you are doing convolution. The other one is actually you are solving difference equation. Okay, that's our input signal and output signal. So how about our filter? So our H. So this is actually our H. So this is a H. So when we have the impulse response, so we can analyze the in Z domain, right? So how to do that? Let's go here. For FIR, so we can do the z-plane H1. Okay, actually there's a few other options to do this. So, but we can plot the z-plane using this function z-plane. Okay, let's try to plot that figure z-plane of H1. Let me see if, okay, that's all. So this is a z-plane. So we have actually 3 poles. And all the poles is actually at z equals to 0. And this is actually our zero. So we have 3 zeros. So what is the value of these zeros? So this actually the x, the real value is 0. The imaginary value is 1. This one, the real value is -1. The imaginary value is 0. And this one, last one is the real value is 0. And that one is very close to 0. Okay, because this is a digital system. Our computer is a digital system. It doesn't get 0. It get very, very, very close to 0. Okay, and the imaginary value is -1. So how do we get that? So actually, what you can do is this is the same thing. If so, how do you get zeros, poles, and zeros? Okay, so because we have our Hn. What is the Hn? Hn is a 0.25, 0.25, 0.25, 0.25. So if you do the Hz, okay, actually you will get 0.25 plus 0.25 z minus 1, 0.25 z minus 2, 0.25 z minus 3. So you will get that one. So you find the roots for this one, find roots. So which is, I can do this, roots of H. So this is actually the roots. So you can do that on your calculator. So this is the first root, -1. This is imaginary 1. This is imaginary -1. Or this is, MATLAB put it as an I. Okay, so either I or J, you can use either one. So this is -1 plus 0i. Okay, so that's how it is plot. And what is the ROC for FIR system? The whole thing, except z equals to 0 in this case. Okay, so that is actually on z-plane. So how do we plot our H on time domain? So, that one will be easy. So actually, you can do this plot. And how many samples that we have? So we have 4 samples. So it's supposed to be up to 3. So 0, 1, 2, 3. So you have 4 samples. And this is what you get. Actually, this is not good because we have only 4 samples. Okay, so a better plot is actually using stan. So now you can say that at sample 0, so you have 0.25. Sample 1, it is a 0.25. Same thing at sample number 2. Same thing at sample number 3. Okay. What is wrong with this plot? There is something wrong with this plot. So can anyone give me what is wrong with this plot? Someone? Before we start, so this is my last question for this session. So what is wrong with this plot? So we are plotting discrete time system now. Okay, why this is a system? Because this is Hn.
The index is,
The indexes, why? Or what happened here?
there's no index n equals 0.5, but they still show.
Yes, correct. Very good. Okay. So we shouldn't have this thing 0.5, 1.5. Actually, this one doesn't exist. It's supposed to have only a 0, 1, 2, and 3. Okay. So we shouldn't plot this one. It seems that if you plot it this way, so at 0.5, the value is 0. Right? So how to fix that? So actually, it's quite easy in MATLAB. So you can do actually one function, which is what we call a xticks. And okay, starting from 0, and then 1, 2, and then 3. So now this is perfect. Okay. Of course, not 100% perfect because, of course, you need to label the x-axis, you need to label the y-axis, and to be better, you should put a title to it. Okay, so because a plot without a label is not complete. A plot without a label is not complete because if it doesn't have a label, so we do not know whether this is actually, is that discrete time? Is that time in second? So we do not know. So that's why labeling is very, very important. Okay, but now at least we have fixed that. So there's no 0.5, 1.5, 2.5 anymore. Okay, because that's not possible for discrete time. For discrete time. So everything's supposed to be in integer. Okay, so we will stop here. So we have seen 2 examples from this first session. So on our next session, so we will start next session at 12, 5 minutes. Okay, 5 minutes. So we'll go for a new chapter, which is inverse Z transform. Okay, so thank you. We see you again at 12, 5 minutes.
Thank you, Data.